Hello friends, I am Dr. Madhukar Jadhav. In the last lecture under the stream sanitation part 1, we have studied what is meant by stream sanitation, then self-purification of natural streams and factors responsible for self-purification. In this lecture, we are going to study zones of pollution in the stream, oxygen sac curve and Steter-Phillips equation. So starting with zones of pollution in the stream. The self-purification process of stream polluted by wastewater can be divided into following zones. First zone is zone of degradation, second zone of active decomposition, third zone of recovery, and fourth zone is zone of clear water. So these four zones we are going to study in detail. So before that we are going to see the sketch of zones of pollution in stream. So in this sketch various zones are shown. First one, clear water, then zone of degradation, zone of active decomposition, zone of recovery and zone of clear water. Now see, when or before a disposal of wastewater into the stream, that zone we can call it as a clear water zone. Then when we are discharging the wastewater into the stream, then at that particular point where the oxygen level is we can say 100% saturation DO is present, and as soon as wastewater is discharged, then DO level start depleting. So it is shown by an inclined line. The DO is goes on depleting, which is present in the stream water, and a point will reach where there is a minimum DO present. So that particular zone is called as zone of active decomposition. So in zone of active decomposition, the maximum depletion of DO will take place, and after this point the regaining of DO starts. So that is shown by this particular inclined upward line, and this zone is called as zone of recovery, and a point will reach where the DO is equal to the previous DO of clear water, and that particular zone we can call as clear water zone. So depending upon the zones, say zone of degradation, in this floating solids will be present. There will be a bottom sludge, then color getting turbid. In zone of degradation, the wastewater or the water of the river or stream will be darker and greyish in color. Then different gases, maybe CH4, CO2, H2S will be emitted from that particular water. Then zone of recovery, here the turbidity at the bottom and sludge will be also at the bottom, and after that the DO gets recovered, hence the water will be looking clear water with no bottom sludge. So these zones are explained in the next slide one by one. First one, zone of degradation. This zone is found for a certain length just below the point where sewage is discharged into the stream, means the water is flowing to the river, and at a particular point we are discharging the wastewater. So that particular point where we are discharging the wastewater, that is called as zone of degradation. This zone is characterized by water becoming dark and turbid with formation of sludge deposits at the bottom. DO is reached to about 40% of the saturated DO, means if previously DO is 100% saturated, then DO will deplete to 40% of saturated DO. Next one, there is an increase in carbon dioxide content in that particular water. Reoxygenation occurs but is slower than the deoxygenation. Next point is these conditions are unfavorable to the development of aquatic life. Algae may die, but some fish may be present feeding on the fresh organic matter. So this is zone of degradation. Then second zone is zone of active decomposition. This zone is just after the degradation zone and marked by heavy pollution. Means in this zone there is a heavy pollution of stream water takes place. The water looks like a grayish and darker in color. Then DO concentration falls down to 0 in this particular zone. Then active anaerobic decomposition results in formation of hydrogen sulfide, CO2, N2 and methane, which leads to objectionable odor to that particular stream water. Then there may be chances of scum which may be seen on the surface of water. Fish life is absent, but aerobic bacteria at upper and anaerobic bacteria at lower of that particular stream depth may be observed. Reaeration with rise in DO concentration to 40%. So this is zone of active decomposition. Then next zone is zone of recovery. In this zone, the recovery of dissolved oxygen starts. In this zone, the process of recovery starts from its degraded condition to its former condition. The stabilization of organic matter takes place and the BOR of wastewater is reduced. The DO content rises to 40% of the saturation DO. The bacterial load decreases as the food supply for bacteria is reduced, and near the end of the zone, microscopic aquatic life may reappear. So this is zone of recovery. The last zone is a zone of clear water. In this zone, the natural condition of stream is restored, with the result of water becomes clear and attractive in appearance. DO rises to saturation level and oxygen balance is attained. The aquatic life prevails in this zone. So in this zone, whatever the water before the disposal of waste, the same water will be available in clear water zone. The next one is oxygen sac curve. When we are discharging the wastewater into the stream, depletion of oxygen takes place, and that depletion is shown by different graphs. One is a darker graph which is shown like this. So when or at a point where we are discharging the DO depletion starts like this, and the point DC where there is a critical DO, or we can say least concentration of dissolved oxygen, and it remains for certain length of the stream, and after that the DO regain or DO increases like this, and after certain length of the stream DO is same equal to the DO before disposal of the wastewater. So this is called as dissolved oxygen curve. Second one, if the natural processes are not present for the DO increase, then the line blue is shown for the cumulative addition of oxygen. So this is the blue line like this, and there is a red line, the depletion of DO takes place. If the natural conditions are not over there favorable, then DO goes on depleting. It is called as cumulative oxygen depletion, and this is the R0 is the slope of this particular line. So in the next slide we are studying regarding oxygenation and deoxygenation terms. So oxygen sac curve we have seen. Oxygen sag or oxygen deficit in the stream at any point of the time during the self-purification process is the difference between the saturation DO present in that particular stream and the actual DO content at that particular time. Or we can say oxygen deficit is equal to saturation DO minus actual DO. Normal saturation DO value for fresh water depends upon temperature, and it is 14.62 milligrams per liter at a temperature of 0 degree centigrade, and DO will be 7.63 milligrams per liter at 30 degree centigrade. When wastewater is discharged into the stream or freshwater, the DO content of the stream goes on depleting, as we have seen in oxygen sac curve. This depletion of DO content is known as deoxygenation. Depletion of the oxygen content is known as deoxidation, or you can say reduction of DO. The rate of deoxygenation depends upon the volume of organic matter, time available for decomposition, and the temperature of stream water or river water. The depletion of the DO content of the stream with time is represented by deoxygenation curve, which is shown in the previous figure. The ordinate below the curve indicates oxygen remaining in the natural stream after satisfying the BOD present in the wastewater disposed. Though the DO content of the stream is gradually consumed due to the BOD load, atmosphere supplies oxygen continuously to the water through the process called as reoxygenation. Means whatever the oxygen depleted, that oxygen regained by the process called as reoxygenation. So whatever the atmospheric oxygen is there, it gets mixed with the stream water. Along with the oxygenation, reoxygenation also continuously takes place. So whatever this oxygenation rate is there, it depends upon first depth of the water in the stream. If the depth is less, then the rate of reoxygenation is more. If the depth is more, the rate of reoxygenation is somewhat less. Velocity of flow in the stream. If the velocity is more, the rate will be more. Oxygen deficit below saturation DO means to what extent the DO has depleted, on that also the reoxygenation rate will depend. And last one is the temperature of water. Depending upon the temperature also, the rate of deoxygenation will be more or less. Now next we are going to study the Stitter-Phillips equation. Stitter-Phillips equation is the equation which is given or expressed for finding out the dissolved oxygen in the stream at a particular time. So the equation is like this: dt is equal to K to L0 divided by R minus K into bracket 10 raised to minus Kt minus 10 raised to minus RT bracket complete plus D0 into 10 raised to minus RT, where K is equal to BOD reaction rate to the base 10, R is equal to reoxygenation constant to the base 10, D0 is equal to initial DO deficit at the point of waste. At the point of waste discharge at time t is equal to 0, it is a classic Stitter-Phillips equation for oxygen sag, which is most commonly used in the river analysis for knowing the DO. So in this lecture we have studied different terms which are related to the oxygen sag curve. Then we have studied different factors which are responsible for the stream sanitation. We have seen the deoxygenation and reoxygenation, and finally we have studied regarding Stitter-Phillips equation. So this is all about in this lecture.